from EDAB Research Institute, and I'm going to present our paper titled Dialog2Flow, Pre-training Soft-Contrastive Action-Driven Sentence Embeddings for Automatic Dialog Flow Extraction. So the goal of our paper is basically how to extract, or is related to extracting dialog flows automatically from a collection of dialogues. And basically, in simple words, will be how to extract canonical steps from conversations automatically. And more precisely, we wanted to release a pre-trained sentence encoder, pre-trained for this purpose, because it's not easy to define how to pre-train models for these tasks. So we decided to focus only on individual to begin with in this initial work. We decided to focus only at utterance level, which is individual steps level, to train a sentence encoder that will encode elements in a latent space, capturing these canonical steps. But what these canonical steps are, basically. That's a hard to answer question, but we decided to leverage on task-oriented dialogues literature. And in task-oriented dialogues, there is the concept called dialog act that is basically the type of utterance with respect to the communication of intent. In this case of this example will be the words bolded here. Like for instance, I'm looking for the transport unit department, please. The dialog will be inform. And the other concept that we also use is the slot, which is basically the pieces of information in the utterance that is basically related to the task being addressed. In this case, for instance, for the first utterance, I'm looking for the transplant unit department, please. If we put together the dialog act and the slot, we get the inform department action that we call action. And this can be seen as atomic canonical steps, because if we see the sequence of canonical actions, we see the sequence of canonical steps. Like for instance, inform first, the user informed the department, then the system requests more information, then the user requests phone, the system inform phone, and the user confirm phone, and so on. So why not use this annotation to actually train a sentence encoder that actually can encode this type of information? If we manage to do this, the similar way that in which we have, if we have a collection of dialogues with this annotation, we can extract the flow. If we have embeddings that encode this type of information, we can cluster them and also get we can try to extract a similar flow. To do this, we actually managed to unify 20 task-oriented datasets under a standardized dialog act and slot annotation. We ended up with a corpus of 3.4 million utterances that contains 18 dialog acts and around 500 slot labels. This gave us a total of around 4K action labels, would be like the canonical step labels that span across 52 domains. Once we have this annotation, next step is to train the sentence encoder. To do this, we use supervised contrastive learning, the standard supervised contrastive learning on one hand. That basically what it does is try to map elements that utterances that have the same label to this similar region of the latent space. Like for instance, in this example, we have your phone, please, which has the label request phone. It will be mapped to this region in the space. If we have the next utterance, okay, may I have your phone number, please, which has the same label. It will be mapped to a similar region in the space because they have the same label. And here, let's say we have a third one, which is okay, thank you very much, which has the label thank you. It will map to a different region of the space, a different region of the space. And the way it does the supervised contrastive learning does this is basically through the supervised contrastive loss, which basically tries to minimize the distance of elements that have the same label at the same time as maximizing the distance of element that has different labels. So we'll have something like this every time we backpropagate. But the problem with this label is that since we have 4K labels and we will know that this label will have slightly different name, but equal semantic or similar semantic. Like for instance here, suppose we have this utterance that please provide me with the phone number, which has the label request phone number instead of request phone. We know that this is semantically equivalent, but the problem is that with this loss, we will get this one mapped to a different region of the space simply because they have different label. So in our work, we propose a new equation, loss, that is soft-contrastive loss, supervised soft-contrastive loss, because we replace the target distribution by a distribution that is proportional to the semantic of the labels. And using this label, basically, we'll try to minimize the distance of elements that, now we don't have, no longer have the notion of equal of different labels. What we have is different degrees of similarity, but will be given by the semantics of the label. So at the end, we will get this utterance map closer to the original ones because they have labels that have semantically similar or almost the same semantics, basically request phone number, request phone. So once we have this, the next step, how do we evaluate this sentence encoders? And in the paper we show that we evaluated basically to answer the following two questions. How does our soft-contrastive loss compare against the original one? And the other one is what happened if we were to use other available sentence embeddings for the same task, for these tasks? What will happen? And we show that in the paper that we evaluate this through three different evaluation metrics or approaches. One is using few shot classification, prototype-based few shot classification that only uses the distance known. There is nothing to be learned, only using this distance of embeddings to classify the other ones. Anisotropy, which is a geometric metric that compares the average distance between elements that share the same label compared to elements that has different labels. And ranking-based evaluation. In the paper, we answer the first question: how does compare our loss with the standard one? And we see here like the first two. The first one is the proposed one in all the plots, and we see that it always outperforms the second one, which is the original supervised contrastive loss. And regarding the second question is basically what would happen if we were to use other sentence embedding for the same task. We see that they will underperform. And here in the paper, we are comparing against most of well-known sentence embedding, like sentence embeddings, like sentence BERT, standard like old school like Glove, also OpenAI new recently released text embedding 3 large, and also dialog embeddings like these E or space. And one of the main hypotheses why the soft-contrastive loss is working better is like here we have a projection in a sphere of the embeddings, and they are color-coded by the ground truth action or the ground truth step that they encode. And we see that here, although using contrastive, supervised contrastive loss, we are grouping the elements together, the elements that have the same, they share the same action. With the soft-contrastive loss, we not only are grouping the actions together, but we're also rearranging the elements in a better way in the space. Like for instance, here we see that the orange dots here represent informed price, and the blue ones informed name. And we see that between informed price and informed name, we have the purple, which is informed class, price, and name, and so on. And while if, for instance, if we were to use sentence embeddings like BERT or OpenAI, we will have like semantic clusters, but not necessarily clustered by the steps. One example will be like, for instance, we'll have sentences that talk about phone numbers, but one thing is to inform phone number and the other is to request phone number. Because it's lacking that's the intention, the communicative intention is lacking, right? If you only consider sentences, like semantics of the sentences. And just to show one example of this, we have here an example for the query, for the ranking-based evaluation. We have the query your phone please, which corresponds to the request phone number step or action. And we see that if we were to use SentenceBERT or OpenAI text embedding, 3 large will be similar result. We are retrieving utterance by the semantics, and then we get things that talk correctly resemble the same step, but also things that talk about numbers, like can I get please your ID number, or for instance, this one is it was evaluated on spoken was that it was shared by ASR. That way we see things that make no sense like this because they are ASR errors. Or may I have your phone name in case of our cooking at the table, or okay, and your car number. Like we are retrieving utterance that talk about numbers. And if we use, for instance, the Dialog2Flow embeddings, we will get utterances that all of them resembles the same like communicational step, which is request phone number. And we also evaluated in the task of the target task, which is basically the Dialog2Flow extraction. And this is the real flow that we extracted with ground truth annotation for the hospital domain in spoken was. And we see that we have how the conversation flows, like the user greet, the agent greet, the system greet, the user informed the issue, the system may request more information, or the user may inform the department he wants to contact with. Then the user confirm the department or request more information, then request the department, and so on. They inform the number and so on. If we were to use semantic embeddings, like for instance, this is the plot we get using the OpenAI text embedding, we see it's much smaller and it's not capturing the same flow, because here we are only capturing like semantic steps. And this is the same with SentenceBERT, similar result. We are always capturing like a fewer number of steps in the conversation. And if you see, it actually breaks the flow of the conversation. Something similar happens if we use dialog sentence embeddings, like from Amazon, let's say, is embeddings trained from Dialog. We have a better flow that compared to semantic embeddings, but still is not capturing the same complexity as the original one. And we see here that with the Dialog2Flow, we get, although not exactly the same flow, we get a flow it has this more or less the same complexity, and it captures more or less the same flow. And we see like here, of course, we cluster the utterances, and here we are showing the cluster ID, but next to the cluster ID, we are showing the utterance close to the centroid. In the paper, in the appendix, you can find information that, for instance, how to use LLM to assign a canonical name to each one of the clusters. And something from these results, a common pattern that we noticed is like the other embeddings, they have a tendency to underestimate the complexity of the conversation, because they only capture either semantic steps or they capture steps from dialogues embeddings that has to do with the context of utterance in the conversation. And we see that with the proposed soft-contrastive loss, this plot basically is the similarity with the reference graph, an average across all the domains of spoken words. We see that with the Dialog2Flow, we get above 90% of the similarity in terms of number of discovered actions or number of steps extracted, compared to the other ones that the other embeddings we get around 50% of the steps. So we get like half the complexity of the domains, and actually it breaks the flow. So the final remarks is like in our paper with our work, we release a new embeddings like Dialog2Flow, pre-trained for Dialog2Flow extraction. We also introduced the soft-contrastive loss, and we also released the dataset, the corpus that we obtained by unifying 20 task-oriented dates. So that's it. Thanks for your attention. Here you can scan the codes to get access to the paper, to the Hugging Face models and dataset, or also to access to our GitHub repo, in which we are also releasing the code to replicate the experiment, and also to convert any corpus of dialogues without any annotation to flows with any embeddings that you want to. And in case you have any doubt, you can contact me by email to this address. And okay, that's it. Have a nice day.